Hello everybody, this is going to be a bit of a longer video today. I'm going to go through an interpretation from start to finish, including loading all the data, selecting databases in our key well, and then going all the way through the cutoffs interpretation and onto our final plot. So let's get started. As you can see, we have the program open here. We have a number of databases and projects loaded, but to get started, what we want to do for this example is walk you through some of the data loading process. So first of all, let's take a look at our actual files here. So here I have a bunch of LAS files, and you'll notice they are in a zip folder. So you can see that's just a zip folder. You'll notice that there's only LAS files in that folder. We don't want to have anything else in there. It's okay to have subfolders, but you don't want to have, a text file, Excel files, etc. So it's just got to be your LAS files in there. We also have our well header file here. So let's just expand this out a little bit. So the thing to notice about the well header file, we have the required columns here, which are our API or UWI number, our wellhead lat, and our wellhead longitude. And then we have, several optional columns out here. And then for our tops, once again, we have the API number, the formation, and the measured depth of the top. Now, what's important to note here is that our API numbers match exactly. They have the same number of digits, and they tie together with what's in the project. And this is how we tie everything together. The API that's in the LAS file to the API that's in the well header file to the API that's in the tops file. So now that I've showed you what these files look like, let's go ahead and close those up, and we're going to load some of these files. So we're going to go File, and let's start off. Let's upload those logs, because that takes a few more seconds. And I'm just going to call this my first project log database, and I'm going to say choose here, and that file was it's here on my desktop, so I'm just going to say open. And we have a few options here, strip spaces and dashes. I would almost always recommend to keep this on, because a lot of times vendors may put in a space or a dash in the API number, and if you don't have that option checked, you may run into some trouble if you don't have those spaces or dashes in your spreadsheet. And then we also have the option to either truncate or pad out API numbers. And so we're going to set these to 14 digits. So let's just hit OK. And that file will upload, and then it will process. So now we're going to go File. And we're going to say Upload Well Headers. And we're going to once again, we're going to call this my first project. I like to give all my databases the same name. That way I know they're related, they're tied together to the first project. It helps me for data management, but you can obviously give them any name you want as long as it's a unique name. So we're going to choose the file. We're going to come over here, and we're going to choose the CSV version of this. And the reason I'm choosing the CSV is it has one extra option that I want you to see here. Otherwise, the CSV and the Excel loads will be very much the same. So we've got our name, the file we've selected. There's this date format, and we're going to come back to this. So when you're loading an Excel file, you don't have to do this, but when you're loading a CSV, you need to specify the date. And then we need to specify the number of header rows. So we're going to say one header row. Here we have a preview of our data. We just see the first 10 rows. And then we see those same options about stripping spaces and dashes and padding and truncating APIs. So let's leave that the same. And then what you do is you just come here and you match up your column names. API to API, wellhead lat to wellhead lat, wellhead long to wellhead long, etc. We go through these, we get to Spud Date. Now the Spud Date I have in here, it's the 4-character year followed by 2-character month followed by 2-character day, which is what we see in here. However, if you had these separated by slashes, you'd need to replace these dashes with slashes. And so on, and we come through and we get to these, and finally we have a couple of things that aren't in here, such as the field name, the horizontal indicator, and the basin. And for these, we check, we see, well, if it's not in here, so we select ignored, and then we hit OK. And then finally we go File, Upload Tops, and we're going to once again give it the same name, so that way we know that it goes with this project. My first project, and then we're going to select the tops. We're going to hit OK, tell it one header row, and now we're going to hit OK. And we can see that our log database and our well database have already finished, and they're now visible over here. So if I click on my first project.log database, we can see it has a list of all the API numbers that were imported, the start and the stop depth, as well as the summary of the curves. If I click on my well database, I can see that this will just take a second for the preview here. And we can see that we have a list of the API numbers, the well name, and then some of that header information here. And then finally, if we click on the tops file, so my first project.tops, so we can see there's two columns here. There's imported tops, which has API formation and depth, and there's user edits. And if I come in and I make edits and I save those into my project, they will then show up here in this second column. Okay, so now that I've got those, let's go ahead and close those. So we feel good about that worked right now. So now we're going to go File, New Petrophysical Calculation. I'm going to call this my first project. I'm going to hit OK. All right, and so now this opens up a new blank workspace. So the first thing we want to do is we want to associate those databases that we just loaded with our project here. And so we come over here to the databases area on the top right hand side. We're going to say select database, and we're going to say my first project.log database, my first project.tops. Okay, and so you can see that as we've done that, we've populated our well list, and the map is zoomed in to our area of interest here. Okay, if things aren't showing up, the best way to troubleshoot that is to go in and look at those databases and make sure your API numbers all have the same number of digits. Also, you can come in here and check your filters to see if maybe you're accidentally filtering out a bunch of wells here. Excuse me. So, and you can check to see, do I accidentally have horizontal wells? Do we just have vertical wells, etc. So now that we've got that, we can have this little asterisk beside our project name here. So let's go ahead and save this. And if we click on a well here, here it should bring up the logs where we see, we have our full suite of logs. We have our top showing up. So the data is definitely getting in there, and the project's working for us. So, in terms of next steps, there's two next steps. It's up to you in what order you want to do these, but we need to set up our zones for our project, and we need to select our key well. For this, I'm going to set up the zones. So if we go Edit Zones, this will bring up a dialog, and it'll ask us if we want to compute zones automatically or customize zones. And if we go to compute zones automatically, that's essentially just going to leave our zones exactly as they are. And if we do this, when we go to a module that actually allows us to interpret on a zone by zone basis, like let's say our clay volume module, what we'll see is that we go from, for example, the top of our Lewis to the teapot. We go from the teapot to the Parkman to the Sussex. So we're going top to top. And if I were to, so I want to point out here, we have the teapot and then the Parkman and the Sussex. If I delete out the Parkman, we'll notice it disappears from the list up here. And now our zone would go from the teapot all the way to the Sussex. Now this may not be the behavior that you desire for your project, because it means if you went to go make a map of the teapot, it would now be too thick. So I am going to click Display Original Pics, and I can see that Parkman there, and I'm going to add top, and I'm going to add the Parkman back, and then I can say Revert Parkman Edit to get it right back where it was, and now we can see it's back in our list. So probably what you want to do, and what most of us want to do, is we want to have an apples to apples comparison across the plate where we have Lewis to Teapot, Teapot to Parkman, Parkman to Sussex. So a defined top and a defined base. And if there is no Sussex, then we're not mapping from Parkman all the way to Shannon. We're just not using that value for our gridding. We'll still be doing the calculations, but we just won't be using it in our gridding and our summaries. So the way we do that is we go to Edit, Edit Zones, and instead of saying Compute Automatically, we say Customize Zones, and then you'll have the choice of either adding zones or initialize from tops. If you only have a handful of tops, I like to say initialize from tops, but if you have, you know, let's say 15, 20, 30 tops, you may want to click Add Zone here and then start adding your zones one at a time. For this, I've got about 10 tops. I'm going to say initialize from tops. And then it brings up this dialog, and it says Lewis, starts at Lewis, ends at top of next zone. And it says, you know, that essentially for all of these, you know, Teapot starts at Teapot, ends at top of next zone. And that's the default behavior, and that's what we want to modify. So we're going to click Edit and Zone Top. So, you know, we have the display name, the zone top, and then we're going to say End at specified top, and we're going to select Teapot. We're going to say Apply Changes. And now we're just going to go through and we're going to do this for each of our things. So we'll go Teapot to Parkman, apply changes. We go Parkman goes from Parkman to Sussex, apply changes. Sussex goes from Sussex to Shannon, apply changes. I'm just going to keep running through these. You know, we want to set this up for all of our zones of interest. And you know, if you have subzones here, you can certainly combine subzones. If you have, you know, tops from multiple interpreters, you can put multiple tops in here. So if you had, you know, like Niobrara picked by Bob and one picked by Tom, you could, you know, have those both be the sources for the tops. So that way, you know, you can have a little bit of control over precedence and whose tops you want to use more. So we do have a lot of options for that. That's also very handy if you are working with an angular unconformity where you may have multiple tops that define the base of a zone. You know, so there are use cases where you probably want to define, you know, multiple tops or multiple bases depending on the nature of the problem you're dealing with. So here we go. We're almost done here. Looks like we missed one zone here. We missed the Carlisle, so let's put that going to the frontier. Okay, and so now we look at these, and they're all going top to base, you know, top to top instead of top to the top of the next zone. It's set here. We have the Dakota, and this is our last one. We haven't picked any tops in this project below the Dakota. So what it is we're going to do is, you know, for this area, we're mainly concerned about the first 100, 200 feet of the Dakota. So we're going to come in here and say Edit. We're going to say Fixed Thickness. And we're going to set this at 200 feet, and we're going to say Apply Changes. And now that we have all this in here, we can hit Apply. One thing to note is you need to have these in the correct stratigraphic order. If you need to move one, you can grab it and you can slide it down. You can grab it and slide it up. All you do is left click and hold on those dots, and then you can move it to wherever you want. Then we're going to hit Apply, and now we're going to save. And to save, you can either go File, Save, or you can hit Control S. Okay, so now we have our data selected. We have set up our zones. And so now the next step is to choose our key well. So Danomics functions on a key well, and the reason we do that is you enter parameters in for your key well, and then those parameters can be used and accessed by all the non-key wells in your project. So the idea is that you interpret once, we build up a blueprint of this interpretation, and then we can apply that blueprint across your project to make sure that every well gets its own custom interpretation. So when it comes to selecting a key well, you don't want to go out and select the best well in your project. You want to select a well that is representative of your project. So don't choose a well just because it has 200 feet of net pay in your zone of interest and all the other wells only have, 10 feet. That's not a representative well. You want to find a well that's representative overall. You want to find a well that has a majority of the stratigraphy available, and you want to find a well that has a relatively full data set. So in this project, pretty much all the wells have really good coverage over most of the stratigraphy of interest. The one thing you can do is you can come up here, and we have some pre-built filters for like a triple combo or a quad combo. So let's select that triple combo here, and now we have our filtered data set, and we can either go through and we can scroll through wells, clicking on them in the list, inspecting their data. We can look at them in a cross section. There's a number of ways we can do this. I've actually got one already picked out here, and mine's called the Mykonos well. So I'm just going to come up here to the search box and type in Mykonos, and we can see the search is adaptive, and it helps us find that well right away. So now we click on that well, and here we are at the Mykonos well. And so we want to make this our key well. And so I'm just going to grab this UWI here. So let me just copy that. And I'm just going to Control-C, click on the little edit pencil, and paste it in there. And so now that I've got that pasted in there, you can see here it is listed as our key well here right underneath the filters. And you can also see that on the map, it's our key well icon, and it's also now highlighted in our well list. So now we have our zones edited, our database is loaded, and our key well selected. So this is once again a good time to go ahead and save our project. And there's a couple other things that I want to do before we really get started with the interpretation in earnest. First of all, I like to rearrange my windows a little bit. Obviously, you can drag and drop the dividers. You can rearrange where windows go, etc. So the layout's up to you. You can also hide away the databases tab and the filters tab if you want to give yourself a bit more screen real estate. What I like to do is I like to put the well list down here on this tab as well, and I like to remove this window, and so that way I have plenty of room for my parameters here, and plenty of room for my maps, cross sections, tables, and well list, etc. So now that I've done that, I'm going to get started on this interpretation. So when we're first getting started with a project, we've got everything selected, we've got our key well. So really the heart of the project lies within this drop-down menu right here. So this module selection menu, as we call it, it walks you through the petrophysical workflow that you will apply, where you go from a setup through curve normalization, down through your clay volume, TOC, inversion, porosity, saturation, cutoffs. So we're going to start off with the setup. So the setup has some important options here for you. So we have a few options like the curve calculation start and end range. This is mainly aesthetic. This will determine how far above that topmost top and your lowermost top that you want to draw the data. You can see now we're drawing it from top to bottom. I don't really care about this shallow stratigraphy for this analysis, so I'm going to say relative to my first formation top. And we're just going to go, let's say 500 feet above it, so that's going to be a minus 500. And then for our curve calculation end, remember we're only interested in the first couple of hundred feet of the muddy, so I'm going to truncate a little bit of this data as well. So I'm going to say relative to the last formation top, and I'm going to say 500 feet below. Okay, and then we have our statistics window. And the statistics window is important. It is more than just aesthetic. So what the statistics window does is it says, hey, I'm going to come in here to a defined interval range, and I'm going to start pulling statistics such as the median, the P50, the P10, the P90 from your data, and I'm going to use that to help build up this interpretational blueprint. When it comes to how thick this window should be, you want it to be thick enough that it captures a representative snapshot of your stratigraphy. I generally don't go from the start of the log to the stop. I generally try to take a window around my zones of interest. So in this, I'm going to go 100 feet above my first top and 100 feet below. You may actually want to go more or less depending on you know, how thick your zone of interest is. A lot of times people may just import, you know, one top and one base of a zone because they're only interested in analyzing a certain interval. That's fine, but I would then say you need to take your stats window start and top, you know, maybe 400, 500 feet above and below. But for this, I'm going to go from 100 feet above to, let's say, 300 feet below. Okay, so now we have a pretty decent stats window there. You have some options on curve units. You know, we can handle both metric and imperial units. If you enter things in metric, if your data goes in metric, we convert that over to imperial to do the interpretation and all the displays for you. And then finally, we have this option on compositing logs. And what the composite does is if you have multiple logs of the same type, for example, if you had two gamma ray curves, it takes the first non-null value out of our alias table. So we do that for you in the background. We also do a lot of curve name standardization and unit conversion for you. For example, in the background, we will detect if your curves are in percent or decimal, and we'll convert those back to the right unit space. You know, if your curve is, let's say, a density porosity, we'll convert that back to bulk density for you. If it's a density porosity in dolomite units, we will, you know, take that into account and convert that back to bulk density. You know, if it's a neutron curve that's in limestone units or sandstone units, we'll convert everything to the right matrix space for you using the interpretation going forward, so you don't have to worry about that. And pretty much in all cases, I would leave the composite option turning on. And the one thing to note here is when I'm setting these options, I'm setting all these options on my key well. So the key well is my active well, and that's the well that I want to do my interpretation on. So now that we've got our setup done, once again, we're going to hit save, and then we're going to move on. So curve normalization. This is actually one of the most popular modules in our software. I think a lot of people like having a straightforward and fast way to normalize data. So in this, what we're going to do is we're going to normalize a couple of our curves here. Across this area, we're going to normalize our gamma ray, and we're also going to normalize our PE curve. You can normalize, you know, really whatever curves you want to. We have options for all the curves that are used in our workflow moving forward. And you'll notice as I clicked on these, nothing happens in this well, and that's because we normalize everything relative to our key well. So we have some options here. So we have simple shift, simple scale, and advanced scale. So let's just walk through these. If I go a simple shift, it asks me for my gamma ray mid percentile, and the 50th percentile is in there by default. And what this means is it will take the distribution from our key well, it'll find the P50 value, and then it'll take the P50 value from a target well, and it will shift that target well so that it matches our key well. If we use our simple scale, we give it 2 points. We give it a low point and a high point. So in this case, I'm saying the P10 and the P90. And if you do that, then what it'll do, it'll stretch and squeeze and shift your P10 and your P90 values such that your target well will match exactly at those 2 points in your key well. And it's the same thing if we do the advanced scale, except now you give it 3 points, a P10, a P50, and a P90. And the one thing to note about that is it can be a bit of an asymmetrical scaling effect. So we're just going to go with the simple scale. That's easy to understand, and we're going to leave it at the default of the P10 and P90. And what happens is when we go into another well here, what we'll see is we'll start to see a little bit of shading here between our curves. So we can see that, you know, our gamma ray has been shifted, in this case about 7 units lower. You know, here's one that I think should have, here's another one with gamma ray. We can see that we've had a very small shift, just a couple of units. It's hard to even see. So, you know, most of our data in this area is pretty well behaved, and we're just making subtle shifts. And the reason we're doing this normalization is we're doing it because we're interested in making sure that, you know, we've accounted for things like, you know, the generation of tool, vendor, etc. They all measure things very slightly differently. throughout time and across the kind of the universe of service companies. And so we just want to smooth out some of those differences across our project. So you're probably asking now, well, how do I know if I've done a good job with my normalization? There are a couple of ways we can QC that. So we're going to jump over here to our map, and we're gonna ask it to show us a property map, and we're going to say, let's say for example, our Niobrara Formation. Let's look at our the gamma ray normalization RMS. So we're going to start that off, and it's going to run through the calculation. There are other ways we can look at that as well. So while that's mapping up, we can come over here and we can go to our cross-section module, and we can select our gamma ray normalization QC, and we can see that it brings up a cross-section. We'll go ahead and flatten this cross-section, let's say on the Niobrara. Let's zoom in here. And we can see that in most of these wells, we have a very small shift. Here's a well where we have a bit more of normalization, so we're just coming across here. And generally, the red colored shading means that our normalized curve is lower, and the blue colored shading means that we've normalized to the high side. So there we go. And we can continue with this inspection and cross-section view. So in general, we see that most of these have been selected lower, but our normalization has given us some relatively small shifts. If we saw a lot of very large shifts on this, we may want to consider maybe selecting another key well, or looking at whether or not normalization is something we want to do. So the mapping is finished up now, and so let's zoom in here, take a look at our map. And we can see that there are a couple of wells with with a bit of a bigger shift, but in general, most of these wells, we have some very small shifts, and then some shifts of 10, 12 units here. Let's click on a well here. This well has clearly our largest shift. It's about 30 units of shift that we see there. So that's a pretty big normalization. Here we can see that we have another well, where we have a pretty substantial amount of normalization going on. But aside from really those two wells, pretty modest shifts. So let's say we had determined that this shift was too big, and we actually wanted to leave that where it was. So what we could do is we could say, okay, well now we're not on our key well. So let's come over to our well log here, and we say, maybe this shift is just too big here. What we could do is we come here and we could actually just turn the shift off in this well. And now if we do a refresh on this map, it's going to do a local refinement here on the grid. So it's not going to have to run through the entire calculation again. And then we'll see that has dropped. We do have one other bullseye over here that looks quite out of place. And it looks like it may be similar here, where we've actually had maybe a bit too much of a drop here in our normalization, and this could be caused by the fact that this well actually is missing a lot of the shallow data. So maybe this is a well that we also don't want to scale. So we're just going to change that to none, and if we want to do this this localized refresh again, now we'll see that this bullseye should disappear. And so that's how we QC our normalization. We can do it both through the map and through the cross section. And so that's how we've got things set up now. So let's say that we are happy with this. There's maybe a couple of more data points that we could check, but in the interest of time for this video, we'll just hold off on that. So we're going to go back to our key well now. And we'll say we've got our normalization done. You'll also notice there are a handful of parameters here for auto eval. So what auto eval does is it's kind of the opposite of normalization. So when you normalize a curve, you're shifting the curve itself. With auto eval, what it is we're doing is we're looking at how you pick those parameters relative to the distribution of the curve, and then we're moving those parameters from well to well instead of moving the curve. And so, you know, the way that works is if we go to example to our clay volume, and we see the default value for clay here is 20 units. And so let's say we felt that was a good value for this well, but maybe not for all of our wells. So we could come back here to this curve normalization. We could turn on our auto eval. And then when we're at our clay volume in this well, it's still at 20 units. But when we go to a target well, what we'll see is instead of being at 20 units, it's now at 21.55 units. And basically what the software is saying is an equivalent pick of 20 units in your key well is 21.5 units in this well. And so that's what the auto eval does for us. I will say be careful about using auto eval and normalization together. It can be a bit heavy-handed. So just, you know, choose wisely. But the auto eval is an interesting option to play with, and it really helps ensure that every well gets its own customized value. So we're going to go back to our key well here. And just for the purpose of this exercise, we're going to go back to our normalization, and we are going to turn our auto eval on for gamma ray and SP. We're actually not going to really use SP in our interpretation, but we'll go ahead and turn that on there. So we're through with that, so let's go ahead and save, and let's go to our Badhole ID and Repair. So the Badhole, we use we have two objectives here. We want to first of all identify areas where there is washout, but we also want to repair the curves in areas where there are washout. So let's I'm just going to shrink the map here so we've got more room to focus on our parameters. And so, you know, we have four options here for flagging Badhole in our density and PE curves. These are a caliper max criterion, caliper rugosity, a density minimum cutoff value, and a D-row maximum value. And then we can also flag Badhole in our neutron and sonic if we want to. So to start off, let's concentrate on our PE. So if you're looking at a single well analysis, using caliper is a good way to do this. But if you're looking at multiple wells, obviously, you know, there's different hole sizes across the basin. You know, your zone of interest may be in your 13 3/8 in one well, and maybe in your 9 5/8 in another, maybe in 7-inch hole in another. So, you know, we're going to avoid using the caliper, and instead we're going to focus on the rugosity, the row B minimum, the D row for this exercise. And we're also going to flag washout in our sonic curve as well. Although, you know, we're not going to flag it in our neutron, and the reason why is our neutron is pretty stable. It's not very susceptible to washout, so we're going to ignore that one for now, but we are going to pay a little bit of attention to our sonic. And so, you know, when you come in and you want to set these, all these parameters can be adjusted via drag and drop. So, for example, here, if I'm coming into my Lewis zone and I wanted to adjust this, you can see that this value changes as I provide input. So it's drag and drop for all of these. So you can really choose to set these how you want. I'm going to use a value of 0.18. And you'll notice that when I type in here to the default, it changes all of my rows except for the ones that I have already set manually. Now if I delete that one out, now you'll notice that it's gone to the default here. And it's really that way for all of these. I'm just going to come through and set these at a few values, top to bottom. And now you can see that as I've done that, we now have some washout flags that have appeared. So if we zoom in here, we can see that we're flagging washout here across our density curve. And so so now we've marked some of those areas. Now you'll notice there's still some edge effects on these where we haven't caught it with our cutoffs here. So what I like to do is I like to use this pad Badhole flag. And what this does is it adds a few samples to the top and bottom of your washout markers to help just kind of fill in the gaps there. And you can adjust this number up and down, you know, to try to catch a bit more. You can see there's still a few places where we're missing, you know, a little bit, but by and large we've called this. And you know, the repair now, so the repair is automatically done for us. So here we probably had some density values that were just too high, or sorry, just too low. So they're coming in too high of porosity. And we have some options there. We can either take no action. If we take no action, then you know, we don't do anything to the curve. There's no repair done. We can null the values in the Badhole, in which case, you know, here now there is no value, so there will be no interpretation moving forward. Or we can repair them with either multilinear regression or random forest. In terms of which does a better job, they are very similar. The differences between the two methods are exceedingly small. However, you know, these are different methods. You know, random forest, maybe one of the weaknesses of it is it can only return values that are within the range of the return values, whereas the multilinear regression can extrapolate beyond observed values. But the random forest, some people think it gives a more aesthetically pleasing answer because the repaired curve has more character to it. Really up to you. I'm going to go with MLR on this one. The MLR is marginally faster, so you know, if you're worried about speed, maybe you have a really big data set, 15, 20,000 wells, where every second counts. You know, maybe you want to use MLR instead of random forest. And so now we can see our repaired curves across here. So we'll say that we like those. They are what we're looking for, and now we can move along. But before we do that, you know, let's think about QCing our Badhole results. You know, we can look at, for example, a summary map of the Badhole. This will run again. You know, we've made changes in our key well, and that in turn affects all of our wells. So we will rerun the calculation again. And then we can inspect this map, and this map will basically be a summary of how thick the total washout is for this, you know, in this zone for each of the wells. So as that's running, we're going to go ahead and move along to our clay volume, and and get started with this part of the interpretation. So with the clay volume, we have some options here. We have, you know, options to use Vclay from gamma ray, Vclay from neutron density, Vclay from SP as well as MFE. Now, in a lot of tight rock systems, the SP curve, you know, has very little character. It only highlights, you know, maybe the more conventional zones. So for this example, we're actually going to turn off the SP, and we're just going to focus on the neutron density as well as the gamma ray methods. Within gamma ray, you'll have options for using this linear method, but you'll also have some of the nonlinear methods like Larionov, Clavier, and Steiber. And then for help with tracking, you know, we have these lithology presets here. So, you know, I'm going to set some of these up, you know, just so I can keep track here of some of these. So actually a majority of these zones are sandstone reservoir, except for our Niobrara, which is an organic shell, and the Maori, which is an organic shell. Okay, and so once we have those, now let's go ahead and start our interpretation. Okay, and we see our maps finished. So here's our summary of our amount of washout in each of these wells. we can see that, fairly small amounts. There are some wells where there's a bit more washout. So, we could go in and QC those, if we were concerned that we may be flagging too much or too little washout. But for now, we're going to say that's good enough for this exercise, so we can get on with our cross plotting. So here we have a cross plot of our density versus our neutron, and so let's go ahead and set this up. So we're going to click on our settings icon here, and for our formations, we're going to say we want our all these sandstone zones. We're going to go ahead and select. So I'm selecting multiple zones here, and when you've got multiple zones selected, you can change all these parameters at the same time. Okay, so I'm just going to adjust my endpoints here. Since it's a sandstone, I'm dropping my matrix point right on my sandstone matrix point. And then I'm dropping my clay point out here, kind of in a mixed clay system, somewhere between illite, kaolinite, and schmecktype. Okay, now I'm going to turn these zones off. I'm just going to clear all those out there. I'm going to turn on my my pre-zone and my Lewis. The Lewis out here is often a limestone facies, so I'm going to select that. Okay, now I've got that dialed in, and then finally I'm going to look at my two organic shells, the Maori and the Niobrara, and we're going to set our matrix and our clean point here, and then we're also going to set our clay point. Okay, so now that we've got those set, we can see that as we've moved these, it's updated all of these in our table here. So all those are updated, and now we need to adjust our gamma ray values so that they match. So the first thing here is, like, the gamma ray scale is a little bit small. I want to have a bit more room to evaluate things here. So I'm going to click on this settings icon, and this opens up how we edit tracks. So I'm going to change this. I'm going to make my scale a bit bigger. I'm going to change that to 300, but I'm also going to make the track itself wider. Okay, so now I've got more space here. The other way you can bring this up is you can click on the settings icon in the top right hand side, and that'll bring that up as well. Okay, and what I can see is that I am calling everything way too high of clay using the defaults. So the method I like to use, I like to come in here and find one zone and get that zone relatively tuned in. So let's see here. Let's focus on the clay end of the spectrum. Okay, so we see we've got a good match between those two curves. Maybe we can tweak that just a little bit here to get this match a little bit better. Okay, so we'll say that's how we like it. What I'm going to do, so I don't have to go through and adjust each one of these, I'm going to come in and I'm going to type these values to use those as our defaults. And now those are applied to every zone. And now I'm going to go in, now that I'm a little bit closer, and and adjust these one by one. So here, this one we need to clean our gamma ray up a little bit. Okay, we look pretty good here. Maybe a bit high on the clay side still, so make an adjustment there. Here we're a little high here, a little low there. So we're just going to leave that. That's the one that we set initially. Okay, we've got a very good match here. Okay, here our Niobrara is an organic shell. So we're going to need to move that clay point way out to account for all the organic material that likes to have uranium glom onto it that makes our gamma ray quite high. So need to push that out quite a ways. For our Carlisle here, we need to make a small adjustment. And we just keep doing this on a zone by zone basis until we've got an acceptable match all the way around. Once again, the Maori is an organic shell, so we're going to have to move that out quite a bit to try and get a better match. Okay, difficult match here in the muddy. It's a bit of a dirty sandstone. And then finally we come down here to our Dakota. Okay. And so once we've got that match so that we are relatively satisfied with it, we'll be ready to move on here. So there we go. Now we feel like we've got an acceptable match throughout our section, and we're ready to move on. And one thing I'll note is when you're doing these interpretations, the interpretation really snowballs on itself, and what you'll notice is that you'll be able to do each step along the way a little bit faster and a little bit faster. And so, it's a lot of work to get started, but then as you do get started and you get moving along, you'll find that you go through clay, then TOC, then porosity, faster and faster and faster with each module, with honestly less parameters that need to be set. Okay, so now that we have that, once again, we could come over here to our crawl section, and we could choose to QC this using our clay volume template. So we could come and we could QC our work this way. We can QC it through maps. For example, I'm generating a map right now of my average Vclay. In this map, the reason it has to regenerate in its entirety every time is because we're making changes to that blueprint. We're making changes to the key well from which we're building that blueprint that we're applying to all the subsequent wells. So every well is being updated in this change. And so we can come over here and we can inspect wells one by one, make sure that the results really make sense to us, etc. It takes the crawl section a minute to draw, but once it has drawn, we can scroll through here and see that we're satisfied that we're getting consistent picks through all of these. And there's some of them that we probably want to go through and really do some zone by zone tweaks in here. And here's a good example of actually why we set both methods. So here, we don't have neutron density here in the middle of the Shannon, but we do have a gamma ray, and so that allows us to fill in our interpretation. Okay, so now we've got our average Vclay map. So let's jump back to our key well here. If we're on our key well. Okay, and when we look at the values here from our average interpretation, we can see that on the low side we're ranging from about 30% Vclay, on the high side about 50% Vclay. That's a fairly tight range for this type of interpretation, and we can inspect this for a few different formations if we want to. We could go through and check it on a few different ones. I accidentally moved a top when I was messing around with the crawl section, and that's why it had to do a little bit of a recalculation there. So here we can see that in the Parkman, we're going from 30% to about 49 or 50 right here at the top. And we can check this on a formation by formation basis if we want to, and that's how we do the QC step on this. But let's move along with our analysis here. So let's move to our TOC. So with TOC, we have options for modified PASI, our PASI sonic density and neutron overlay, Schmoker, Wernicke, Faust, etc. We are going to, by default, we use the modified PASI. And the idea here is that you want to find an inorganic shell zone and use that to calibrate yourself. And that's the way a lot of these methods work. You calibrate yourself in an inorganic shell, and then that matches you up with an organic shell. And so first of all, let's set some of these parameters. We can once again drag and drop these. So let's say up here, our Sussex is a pretty shaly zone here, and so for setting our modified PASI, we want to try and get our RO resistivity overlay to be about where it's at. And what I'll say is that this is log scale, so it's pretty sensitive to movements here. we want to get these lines to overlay themselves. We see about a 0.15 is about right for our bound water. So let's put that in here for all these zones. Now we can see that the Niobrara is lighting up as well as the Maori for those two. For our PASI overlay methods, so for these, what you want to do is, once again, calibrate yourself in an inorganic shell. And so a value of about 4 is about right for our baseline here for that. We're probably going to be about 85 for our sonic. That actually might be a little bit too high for this well, so let's set that back down to about an 80. Yeah, that looks a little bit better. For our density, we can come in here. That's going to be about a 2.58, I think. Let's see. Yeah, that looks about right. And for our neutron, we're going to need a value of about 0.22, I believe. Let's see how that looks. Okay, that looks okay in there. Yep, and then, so that's how we set those, and you can see we've got all these methods in here. And we can see that we're getting a pretty close answer between our sonic and our neutron. Our density, maybe we're a little bit off on, so we could come in and adjust that a little bit to see if we get a better match. Sorry, I went the wrong direction there. See if we get a better match between these values. So that gives us a bit of a better match. We can explore some of the other methods. There's Vernix TOC, which once again we're putting in a clay density for, and yeah, and with a lot of these density only based methods, you'll notice that we they do overestimate quite a bit relative to like the PASI methods or ones that use other curves. So I will say use those with caution. But you can see we can get a pretty close match, internally between the density-based methods, but they're going to almost always overestimate relative to some of the others. And then our Faust method, no parameters really to set for that, but that's a sonic-based method. So if your area if you happen to be lucky and you have a lot of sonic logs, that's an excellent detector. But we're just going to go back to using our modified PASI, and you can select which method you want zone by zone. You might not want to call TOC in every zone. Like, for example, there's some sandstones down here in the bottom of the section. Maybe we want to ignore those. And we can do that with this parameter here. This is our minimum gamma ray for our shell. So let's just set a value of, like, let's say 50 for this. And that means anything with a value less than 50, we are not going to put any TOC in. So we're going to leave it null there. And then TOCs in weight percent, we're interested in getting it in volume percent, and so we need to do a conversion of TOC weight percent to volume percent. We have a few options there for you. Okay, but that is it for our TOC analysis. So we're gonna move along, and so now we're getting to what I think is one of the most important and most powerful modules within the Danomics platform, which is the mineral inversion module. The reason mineral inversion is important is it allows you to calculate a grain density at every depth step, and this allows you to get a far more accurate picture of your porosity in your system than just setting let's say a matrix density. This is also one of the big differentiators within the Danomics platform. There are really no other softwares that operate at scale that allow you to come in here and do a full mineral inversion. So with that said, mineral inversion can be a bit tricky for people that aren't familiar with it, but in general, we define the minerals that are in our system, the properties of those minerals, and then the curves that correspond to each of those properties. And then we generate a prediction of that curve, and that's how we determine if we've got our mineralogy right. And so the way we set this up here is we start off with some defaults. Not really anything in here has dolomite, and with respect to pyrite, you know, our organic shells have that, but none of our other zones really have it. So I'm going to turn off the pyrite as well. And then if we want to set up our color scheme here, this one, you know, we set it through just clicking on the color palette here. But we've got those turned off on our default zone, dolomite and pyrite. But as I mentioned, you know, we do have some of those in our organic zones. And the way we set that is we come up here to this drop down and we say, all right, now let's set it for the Niobrara. Let's turn on some pyrite there. And let's go to the Maori and turn on some pyrite there. Okay, now you'll notice that we do have one zone grayed out still, and that is the that's this row for the conductivity. Conductivity is optional. You don't necessarily need to use that, but it can be helpful if you want to. So we'll come back to that at the end. So with respect to the options here, we can either use a constraint, a fit, or disabled. Disabled means that it's not used. Fit means that we try to honor it relative to these confidence intervals. And constraint means we force an exact match. And the reason we force an exact match on density and unity is because if those two are an exact match, then our density porosity, you know, using a grain density based grain density or a mineral inversion based grain density, will exactly match. So so it's a way to kind of to force an exact solution there. Okay, so that's how we've got those set up out of the box. We're just going to leave those for now. If you wanted to add more minerals, you can come here and say edit matrix, and you could add a new mineral, you could add new curves, and then when you're done, you just say done editing. So just looking at this, one thing we can say is that, wow, you know, we do not have a good match to our sonic value. We have pretty good matches to the rest of our curves, but not to sonic and not to conductivity. Conductivity is disabled, so that's why we don't have a good match for that. It's not being used in the inversion right now. But let's focus on this sonic. So let's come over here to our cross plot. And so when it comes to areas you can make adjustments, obviously, you know, we know the sonic value of quartz and calcite pretty well. Those are not changing. But our clay, because we're using a generic clay and not an actual clay mineral here, there is some wiggle room on the sonic value of a clay. Also, the value for this is going to change based on the level of compaction. You know, is it an organic shell, inorganic, etc. So there's some things we can set there. What we're going to do is let's start off with a DT clay cross plot here, and for our formation, let's go ahead and say all formations. And what we can see is that really there's very few of our points that get above 100 in general. And here at our highest clay values, you know, so we're out here at 65-70% clay, our DT curve is only at a value of around 80 or 90 here. So I'm going to come in here and I'm going to give this a default value of about 90. And when I make that change, now we see that, you know, the inversion reruns, and we get a much better solution here for our sonic. We can see that the sonic now provides a very close match here to our observed values. You know, that could actually maybe even be a little bit better. So maybe we could drop the sonic value in our clay just a little bit further to improve that match. Okay, so we have that. Now the one thing I'll say is we are not matching our conductivity pretty well, or very well at all. Part of the reason for that is there are some parameters that we need to set for that. So first thing we'd want to set is what's our resistivity of clay. So when we do this, you know, we can see that the resistivity of our clay out here at our highest clay values is about 2, 3, somewhere between 3 and 4 ohms. You know, so, but to adjust that, we need to be able to set our conductivity as, let's say, fit. And now remember, we're looking at a plot of resistivity versus Vclay, not conductivity. Conductivity is typically 1 over your resistivity times 1,000. And so if we think about what that means for a value of about 4 here, that would be, you know, 1 over 4, so about 0.25 times 1,000, so that's a value of 250 there. We also need to consider our water salinity. Here we've got a salinity that correlates to around 14,000, a conductivity of around 14,000, and now we can see that we've got a much better match by adjusting those two parameters. Final thing that we could do here is our conductivity. We're putting a pretty loose constraint on that. We could tighten that constraint up if we want to, and that will make the conductivity curve more important in the inversion. And now we see we get a really tight match here between that. Now the one thing I will say is that this has forced a lot of oil relative to water in our solution, and so maybe we're not happy with that. Maybe our waters actually aren't that conductive in this area. So you'll want to take a look at that to see, try and get a good feeling for exactly how that match should be. And you can see that, well, that actually I typed in a bad value there. Meant to type in 8,000 instead of 800. So you can see that as you're changing that, it's changing the answer you're getting on your saturation. So you can come in and experiment with that, trying to set your conductivity versus, of this. So once you're happy with that, this is a good time to save, and it's also a good time to do a QC because we're going to use a lot of these results going forward. So once again, we could come here to our map. We could say, all right, what do we want to use to QC this? How about our average grain density? And let's say we're interested in that for the Niobrara Formation. And since we've made changes to our key well, it's going to kick off a new mapping job here. And these mapping jobs, let's see, if I click on the little jobs tab there, looks like they're pretty quick in total. That was actually a short one because it was just a single well modification. But here we can see they take about a minute and a half, minute and 45 seconds. Instead of waiting for it, we're going to move along, but we are going to keep an eye on what our average grain density looks like because that affects our porosity solutions. Our porosity affects our saturation, and that's going to affect everything moving forward. So to use this mineral inversion, what we need to do is we need to come here to porosity. And instead of using a default method like our neutron density porosity, we are going to set this to our mineral solver porosity. We have two options here, mineral solver and mineral solver strict. The difference is when you go with the regular mineral solver porosity, you still have to put in your own fluid density, but when you go with the mineral solver porosity strict, it uses the fluid density that is implicit in the inversion. So actually that's the one that I like to go with in most cases. And we do need to adjust our clay porosity. Now this is something that is kind of a personal preference, but I'm going to set that at about 12%, and that affects the difference on how we do our total to effective conversion here. And really those are the only options that we set on our porosity. So that was pretty quick. Okay, so while we were setting that, we noticed that our grain density here came in, and so what we see is this map is incredibly flat, very little variation except for one bust here. So we've been doing everything on our key well. This is a non-key well, so let's go in here. Let's take a look at this one, and we're looking specifically at the Niobrara Formation. And let's go back to our mineral inversion. And so, okay, we can see what's going on here. We don't have a density curve here, and because of that, we are getting an invalid, TOC measurement or TOC estimate. That's throwing off all our predicted curves and our predicted grain density. So we could come in here and go back to our TOC analysis, and we could see in here right now that our TOC is essentially coming up as a null value. Now we do have the Faust method that's available to us, and we're getting a good match. So I'm just going to change for this, just this one well, just this non-key well. I'm going to change this to Faust. Okay, and then when I do that, now we can come back here to our mineral inversion, And now we can see that we have a much better constraint on this TOC, which now that means that we have a better estimate for our for our grain density moving forward. Okay, and you know, we can also come in here and see if there's anything else that we have that we've kind of missed on here. This because we don't have neutron density, we may also want to come in here and look at our clay volume. You know, we can say, you know, maybe we're a little bit low on this well. So let's come in here and, you know, let's check our let's check, you know, how we've set these constraints here. And yeah, and actually this looks like a well where we could probably come in and do, you know, a bit of a bigger tweak, you know, for all these, for how we've set all these. But you know, this is part of the QC process, and this is why we have those tools, you know, built in, like the maps to help us out with this. So once we've got that how we like it, now we can, you know, let's go back forward through our interpretation. Okay, we still like our TOC. We come down here, we go to our mineral inversion now, and you know, we can see that we've got, you know, we're getting a better solution here on the you know, on our TOC. We're getting a better solution on our grain density. You know, we can refresh this map, you know, and hopefully we're going to alleviate that bullseye a little bit. You know, but if not, you know, we may actually have to come in here and maybe even consider changing our you know, changing our solution here to exclude perhaps the quartz in this zone. You know, this is, you know, the Niobrara is pretty limey, but you know, this is all caused by missing data. And if worse comes to worse, we can exclude this well and exclude these results from the mapping. Okay, but either way, we've got our porosity now. You know, we just set that. One thing to note is we want to jump back to our key well here. So let's go back to our key well. Because remember, we're still building up that blueprint. We're still going through our first interpretation. So, okay, we're back here to our key well. We've set that we're using the mineral solver porosity. And we're now moving into our water saturation. So for water saturation, we've got a number of methods available to you: Archie, Archie-FT, Seaman-Do, Modified Seaman-Do, etc. You know, it's up to you which one you want to use, but let's, you know, we are going to have to set our RT clay parameters. Here we're looking at all formations. So if we want to use something like Seaman-Do or Modified Seaman-Do, we need to go ahead and set these. Remember, we said that was about 4 ohms is where we wanted to set that. So, you know, let's expand that out. 4 ohms is actually the program default, so that's already put in for us. The next thing we need to set is we need to go to our Pickett Plot. And here with our Pickett Plot, we can see that we've got some pretty squirrely data in there. So let's turn off all formations, and let's so we can see that here in the Lewis we've actually got you know, some busted values in there. But we were looking at our Lewis and our pre-zone together, and we want to filter out some of this data. So we're going to filter out, so we're going to say not, and that's the exclamation point at, and then we're going to call it our Badhole curve, and we're going to say at, you know, Vclay, and let's say less than about 40%, and we're going to say at VE greater than about 0.03. Okay, and so now we're looking at probably what we consider reservoir quality rock. And on the Pickett Plot here, we want to kind of get a match going through the left-hand side of this data. So let's just turn a few more zones on here so we can, you know, see how let's start with all formations. Okay, so if we wanted to see how that looks, we could say, You know, let's we can lower our M value a bit. We can also lower our RW. And so now we've got, you know, now we've got this bounding our data here. A lot of times, you know, I like to say M is equal to N if I don't have any data to the contrary, although obviously what you'd want to do is, you know, get some core measurements here and core calibrate your analysis. And then we've got all our results here, and really the question is, what method do you want to use moving forward? I like using an Archie Phi-T. One, it's easy to understand, and two, by using a total porosity instead of an effective porosity, we can avoid that whole argument of what is an effective porosity in a tight rock system. So that's how so that's the method we're choosing. That's how we adjust these parameters. And so now, you know, we are ready to move forward with this. And after we set our SW, it's really on to our cutoffs and interpretation. We use the Danomics scripting language here for this. So, you know, at calls out our curve, and the curve name is Vclay. And we're going to say less than or equal to, no, we're going to say about 40% in this area. And then, you know, I'm going to use a total porosity. I'm going to say add my total porosity. I'm going to say greater than or equal to 0.06. And there's two ways we can call this out. We can either, you know, say at, you know, and then we could essentially use this exact thing here. Now the disadvantage of this is I'd always have to type in this Vclay twice, and if I change this to, you know, 42, now this is, you know, not consistent. So what I'm going to do is I'm just going to say at gross res. That means it meets my gross reservoir criteria. And I'm going to do a similar thing here. I'm going to say add SW less than or equal to 0.65 and at net res. And you can put as many criteria in here as you want. These can be raw curves, calculated curves, etc. And then, you know, we can come in here and do a visual QC to see if it kind of passes our sniff test. So let's jump in here to the Niobrara. And what we can see is that, you know, we are fairly high Vclay through a lot of this interval, around 50%. And we can see that we are flagging the lower clay areas as having reservoir in here. So, you know, we could tweak this, you know, these parameters. Maybe it should be a little bit lower. Maybe it should be a little bit higher. You know, there, you know, setting cutoffs is, you know, kind of a you know, kind of a bit of a personal preference. You know, unless you have some data that specifically says a zone flows or does not flow. You know, and even then there's debate on whether or not, you know, is flowing just a small amount of oil, does that make something pay, or does it need to flow economic quantities of oil? But this is how we set it, and, you know, if we want to see about getting rid of some of the little stringers, you can set a minimum height. You know, do you need 2 feet of, you know, continuous pay, 3 feet, 5 feet, or just a foot? You know, it's up to you how you want to set that, or you can disable that option. So once we've got that, now we're going to go back here to our map, excuse me, and you know, we could look at, say, for example, a map of net pay or net reservoir. You know, so let's get that started. You know, so we can take a look at that, see how that maps out, see if there's any discontinuities, and then we can go in and QC that kind of, you know, one at a time. While that is going, I would just really quickly want to show you the volumetrics module. So we're going to set our volumetrics here. And with our volumetrics, the way we do it is we calculate the primary phase, and then the second phase is essentially derived from that using either the GOR or the liquids yield, depending on what the primary phase is, oil or gas. So in this area, it's pretty much all oil in this area of interest that I've picked out. And the GORs, Niobrara's, in this area is about 2,500 GOR. So that's the zone I'm going to choose to set that for. And now you can see that our gas phase, our associated gas, has really jumped out there. There are a couple of options you can choose here. Do you want to analyze on net pay, net reservoir, or gross reservoir? I'm going to analyze on net reservoir, and I'm going to analyze on total porosity. And that's because, we believe in these systems that the frac is going to do a lot of our work for us. And so, now taking that view, if we zoom in here, we can see that our Niobrara has somewhere on the order of around 23 million barrels per 640 acre section, and around 55 BCF here in our key well. Now we can see that in some other wells, we have much thicker net pay, and that would also mean that we consequently have, let's say a much higher oil in place summary. So, as I said, this well was around 23 million barrels. So as we are, and I changed a parameter, remember I changed this GOR, so that's why this is updating. I also changed what we're analyzing on here. So once this shows up, we should see that some of these wells, have, a substantially better looking, in-place volumes. And here is a good example. So here in the Niobrara, we can actually see, that we've got nearly twice as much. And what's driving that is, our porosity. We have much higher porosities in this well. So that's why we're getting that higher in-place volume. And then finally, you're probably going to want to take some screenshots of your analysis. So we've got these pre-built display plots here. So you can come in here and, we have a kind of a final display plot for you. Oh, sorry, I'm not on my key well here. I forgot that. That's why I was wondering why the Sonic wasn't showing up there. And so, you can go through and you can look at these and see, where's your pay, where do you have movable hydrocarbons, what does our mineralogy look like. Okay, and so that is an analysis, start to finish. Now, obviously, one of the things, in this is we were really light on the QC portion. This video has already been an hour and 15 minutes, trying to keep it fairly short here, or as short as possible here. But obviously, you'd want to go in and do more QC on each of these parameters. We can do that via the map. We can do it via the cross section. The other way we can also do it is we can also do it by the table view. And so I'll touch on this right before we go. So table view, we select our columns. And so let's say for our Niobrara zone, that's our main zone of interest here. Okay, so now let's say what are the properties that we're interested in QCing? Maybe we want to go through and look at, things like what is our average, what's our oil in place for the zone? What's our hydrocarbon pore volume? What are our, average effective and total porosities? We hit OK. It's going to build this table up, and then this table's sortable. So we can go through and we can find the highest and the lowest values in here and use that as part of our QC as well. And I find that sometimes this table view can actually be a superior way to try and find outliers here. Especially with things like your porosity. Do we really expect something in this zone to have an 11% porosity? Or let's say one of the areas where we saw that we had some trouble earlier was with our average, it was with our TOC. So, we add that, it rebuilds the table. And, now we can look at our average TOC and say, okay, well, all these values are fairly modest in this area, but if we wanted to go in and QC some of these, you know, for the Niobrara, we could go in, we could just click on this here, jump to our TOC, and take a look to see what's going on. And actually here we see that the sonnet curve is the only curve that goes is kind of through going here. So maybe once again, maybe this is another one where we would choose to switch to the Faust method to get our average TOC. And of course, we can update this table the same way as we update the map. We just hit the refresh there, and it's going to run a single well refinement to this grid. It essentially checks to see what values have changed, and then it will run an update here on just that. We can see that it's finished, and we now have that value in there. And so you can go through and you can check all your output values this way. You can also instead of checking your properties, we could come in here and we could check things like our parameters. So if you remember, we had the gamma ray remapping on. So if we wanted to check and look at those two values, now we can look at our average gamma ray clean and gamma ray clay, and we can see how this remapping has performed. So we got values between about 16 and 45 here on this, and then our gamma ray clay range between 220 and about 352. So we could say, maybe that value looks suspiciously high. Come in here to our clay volume, and we could take a look at this and say, oh, actually, yeah, that value is a bit high here. So let's set that value down a little bit. Gives us a better fit, and now we could redo our local refinement and take a look at it that way. Yeah, so that is an interpretation end to end in under an hour and a half, and now every well in our project has its own kind of first level customized interpretation. As I was saying, obviously you would want to go into your project and do a more thorough QC than I've done here, but for a first pass, we should have pretty good results on most of these. And yeah, so I hope this video was useful to you. I know it's been a bit longer. It's about just under an hour and a half long, but that's about the amount of time it should take you to do an interpretation on your key well and get that propagated out to all of your non-key wells in a project this size. All right, well, I hope you enjoyed it, and remember to save your work. Thank you. Goodbye.